Yeah, this is Mike Mulholland, and today we're going to be looking at um, proving the Pythagorean theorem based on the areas of squares. This is going to be a rather long video, but if you like geometry, I think you'll find it interesting. I hope you'll stick with it. I submitted this Ask an Expert question. I'm going to answer it by showing you how I proved the Pythagorean theorem. At the time, I knew nothing about any other proofs, though I was sure that they were out there. My wife was teaching geometry at the time, including the Pythagorean theorem, and I decided to try to prove it on a whim just to see if I could. So here's some history. This was known by the Babylonians of the Middle East before 1500 BC. I've read that it was first proven by a Greek named Pythagoras, that's where the name would come from, or one of his students, sometime around 500 BC. However, I've also read that the first proof, or at least the one that still survives, was by Euclid, a Greek living in Egypt around 300 BC. Euclid was a brilliant mathematician and is often considered the father of geometry. His most important book, Elements, was enormously influential and was used as a textbook for 2,000 years. There's over 400 known proofs, it turns out, so probably somebody's already done the one I'm going to show you, including one by James Garfield in 1876. That's significant because 4 years later he was elected U.S. president. So my proof has this starting point. So does Euclid's, I now know. I was hoping that you'd be able to visualize this to help you understand my question. I would have included this diagram in the question if there were a means in Ask an Expert for doing that. Written Ask an Expert answers have the same limitation, and that's why I'm recording a video instead. So the basic idea here is that when you calculate squares of the lengths of the sides of the triangle, you're also calculating the areas of three corresponding squares. This one, this one, this one. So if you can prove that the sum of this area and that area equals that area, you'll have proved the Pythagorean theorem. So it helps us start like this. And Euclid went on from there. But I do something a little different. The first thing I do is move a couple of the squares. I move this one over to there, this one up to there. So the result looks like this. And then I take each line within and each line segment and extend it to the edge of the green square, and that results in this. And then I label the intersections so we'll have a way to talk about the various shapes and angles. I didn't bother with these intersections here because they don't play any role in my proof. The things that appear to be right angles at the marked intersections are right angles. Most of them we know that because they're at the corner of a square, like this one. Some of them are at the corner of two different squares. That's this square and this square. C and G are a little bit more complicated, but this is drawn out. So this is horizontal, this is vertical. And so we extend this, it's horizontal exactly. And this is exactly vertical, and so it's going to be a right angle. So once you get this far, now it should start to look a little easier just using some basic geometry. So remember, the area of the green square is z squared because that's the length of a side. Our goal is to show the area of the green square is also equal to x squared plus y squared. So the next step is to divide the shapes in the green square into pieces for which we can readily determine their areas. So how can we do that? Let's start with the easiest part. This inner square here. So you can show that from the diagram that the length of each side of that square is, take this side right here, the side of the blue square, which is x, minus the side of the yellow square, which is y. So that's x minus y. And so we square x minus y, and we get x squared minus 2xy plus y squared is the area of this inner green square. Now the next step is what's left to find the area of it. How can we do that? So if we restrict ourselves to the line segments that are already drawn on here, it's still not so hard. So this area outlined in red right around here, this is what we have to do now. So there's still a number of ways that you could do that, but there's only one way. It results in only 4 pieces, all of the same type, and all of a type for which it's easy to calculate the area. And that's to divide it into 4 right triangles. This one, this one, this one, and this one. So before we start calculating the areas, first we need to show that they're congruent. And here I've outlined each of the 4 of them in red. So if they're all congruent, they'll all have the same area. So we're looking for some combination of equal side lengths and equal interior angles. These are the rules of congruency. And if you're interested in why those work and why some similar sounding ones do not, check out a separate Ask an Expert question that I just first submitted and then answered, called Congruent Triangle Rules. Okay, so what have we got here? First, we know that all of 4 of these have the same hypotenuse because it's the sides of the green square, so it's length z. And the angles, but beyond that, the lengths of the legs are not quite as easy, and angles are really easy. So let's turn to angles. So let's so we know that they're right triangles. So one of the interior angles is a 90-degree angle. But let's look at the others. Let's say this angle right here, its measure is theta. This one is 90. They have to add up to 180. So 180 minus 90 minus theta is 90 minus theta. So this angle must be 90 minus theta. Now, that's a right angle, so those add up to 90. So 90 minus theta, and what would add up to 90? Theta. So that would be theta. And then here we go again, exact same situation. 90, 90 minus theta, theta, and so on, all around the perimeter of this figure. So we add that to our graphs, our picture. And so now we have that additional information. So we have an equal side, and we have all three angles actually equal. So we could use, it has more than enough information to show that they're congruent. We could use, what rule could we use? We use the angle and two angles and a side. Any two of the angles and the side that we know is z, length z. So we can use angle side angle or angle side depending on which two angles we pick. But anyway, we've established that they are all congruent, and so they have equal areas. But what is that area? If we look at this triangle right here, the area of a triangle is base times height. Well, in a way, you could say that the height is at the top of this one, but it's the width of the yellow square, which is y. And the height is the width of the side of the blue square, which is x. So the area of one of them is base times height over 2, which is yx over 2. But we have 4 of them. We multiply by 4, and you get 2yx or 2xy. So the total area of the inner square plus the 4 right triangles around it that's the inner square. That's the 4 right triangles. This cancels this, reduces to that. But it's also z squared. The overall area of the green square is also z squared. So the area is that, but it's also that. We just proved the Pythagorean theorem. And that's that. I hope you enjoyed it. Thanks for watching.